Today, in the first module here, I'm going to talk about what we do when we have the captured CO2. I'll talk about storing it underground. I'll also talk about potential uses of it, and I'm going to talk about a related topic on biofuels, which people are talking, is starting to be a big topic in terms of climate change and has some relation to carbon capture and storage. So let's start with geologic storage, and this is a picture from the IPCC report looking at the various options. So we see here basically this is the geology that we're looking at. So one talks about depleted oil and gas wells. So this would be like where maybe some gas or oil was taken out, and we can use that pore space to put it in. So what these geologic formations are, this is generally sandstone formations where you see the CO2 being put into, and then these this white rock here. This is sort of like a shale formation. You can think of shale like a clay formation. So that it's that sort of like acts as a cap rock for these different reservoirs we may want to put the CO2 into. We mentioned enhanced oil recovery. So this is showing it here, which is a reservoir that contains oil. We put CO2 in. It flows through the reservoir, and it helps mobilize the oil. So when you're taking oil out of an oil reservoir, maybe you only get 30, maybe 40% of the oil out, and then you have to use enhanced techniques. Secondary type of recovery includes water flooding, and then when you put CO2 in, they call it enhanced oil recovery or sometimes tertiary recovery. And what the CO2 does is a couple things. It helps move the oil along, but it also solubilizes the oil a little, sort of loosens it up, like when you put solvent on a piece of clothing. If you have oil stuck in your shirt, you try rubbing it, it doesn't move, but if you put certain solvents on it, it will come out. CO2 sort of acts in that way, and what they do when it comes out, they separate the CO2 from the oil, and they'll re-inject the CO2, and when they're all done with the reservoir, they'll leave the CO2 in the ground. The biggest possibility, and showed by here, these deep saline formations, these contain briny water, and you can put the CO2 in these reservoirs, so they don't have economic value, and you put them in the pore space. We'll talk about the mechanisms, what happens when you put them in a few minutes. And then sometimes people talked about putting it in coal seams, but that's unproven. So it's really depleted oil and gas wells, active oil, and then these deep saline formations are the targets. And so that just summarizes it up here. When we put it in, we want to put it in below 800 meters. Why 800 meters? Because pressure at 800 meters, every 10 meters you go down, you get an atmosphere of pressure. So at 800 meters, you got about 80 atmospheres of pressure down there, and that's where the critical point around the critical point of CO2. So if you're below 800 meters, the CO2 will stay in what we call a supercritical fluid. It's not technically a liquid. Above its critical pressure, it only could be a single phase, but it's liquid-like. So it's a little less dense with water. So when you put it into the ground, the CO2 will want to sort of float up toward the top of these cavities that you're putting it into. It's buoyant, but as I say, the cap rock keeps it in the ground. Over time, you'll have some dissolution of the CO2 into the water, And that can happen on orders of decades, and on orders of centuries in these sandstone formations, you eventually precipitate the CO2 out as carbonate rock. Yes?
Are they worried about change? The soil where you're injecting?
Say it again.
Are you worried about changing like the pH of the system?
I'm not hearing well.
Like the acidity of where you're injecting CO2, is it going to change the surrounding environment?
When you put it in, is it going to affect the environment, or?
Yeah, with like acidity levels.
Okay, I'm still start.
Like around the reservoir.
I'm sorry, I'm still not getting the question. I'm not hearing well there. It's when you're putting it in, are you?
Does it make the environment more acidic?
The environment? Well, I mean, underground?
Yeah, so does it have any impact outside of where you're injecting it?
Oh, okay. So I'll get to some of that. There's, in terms, I mean, down there's really no life. So in terms of that, it doesn't really impact. The biggest impact is something called induced seismicity, which is anytime you inject things in the ground, you get some seismicity. Now, seismicity is associated with earthquakes, but you usually get microseismic events when you inject anything in the ground, and those are not harmful. What people are worried about is these coming into earthquakes, and there have been examples of people injecting fluids in the ground that do cause earthquakes if you don't do it right. So what happens is, obviously there's already fluid in there, so when you put it in, the pressure builds up. And what you have to do is you have to keep a good eye on the pressure. You don't want the pressure to get above what they call the fracking pressure and start cracking the rocks and causing seismic events. Now, when they're doing shale oil, they actually put in water and they actually frack on purpose. So they go above the fracking to open up the pores to let the natural gas come out. But if you do this right, you don't have any real problems. There's been things, not so much with CO2, but sometimes with produced water from oil and gas operations, they do have earthquake problems. It's fairly complex, more than we can get into here, but part of it depends on the geology you're working in the first place. For instance, Oklahoma has had a lot of earthquakes recently due to some of the oil and gas operations, not CO2 injection. So that's one of the critical things and to watch out for. And what it does is it's that pressure buildup, how much you can put in before you get a pressure, really limits the capacity of these reservoirs or how much CO2 you put in. These reservoirs, they show them closed here, but a lot of these are open. They're big and they're long, so the pressure wave will spread out and diminish and allow you to do this, and also it relaxes over time. So we'll also talk a little about injection into basalts. This is sort of a new area. There's a couple pilots, and I'll talk about that also. It's a little different than what I call the traditional geologic formation. So we've had a lot of experience with injecting fluids in the ground or gases, and I'll go through a couple of these. Acid gas injection, show this here. So this is, a lot of this has been done in Alberta, Canada. Once again, you have a lot of oil and gas coming out of the ground, and you have acid gases coming with it. The acid gases are mainly hydrogen sulfide, and there'll be CO2 coming with it. And of course, they want to capture it, so they capture it in the production of it, and then they inject those acid gases back in the ground. So your acid gases, combination of H2S and CO2, the red dots showing disposal into depleted reservoirs, the blue dots into these deep saline aquifers. So this has been going on for 40, 50 years up in Canada. Not quite the scale that we see from what we're going to expect from carbon capture, with the numbers we bigger. We talked about enhanced oil recovery. There's maybe, I think, 80 enhanced oil recovery operations in the United States. Maybe there's some more now, but it's on that order. And so this is going on all the time, so we have a lot of experience there. Natural gas storage is not CO2, but it's natural gas. So in natural gas, the big use in the United States, of course, is in winter. So during the summertime now, when we have excess natural gas, what they do is they put it in these geologic formations, and then in the winter they can pull it out to satisfy the winter demand. And that's done on a very, quite a large scale. And there's been commercial carbon capture and storage projects. Show a couple here. I mentioned yesterday Insula. This is the BP operation in the Algerian desert. It's not in operation anymore. This was into a depleted gas reservoir. It was fairly tight rock there, and the reservoir really wasn't that great, so they basically filled up capacity after a number of years and stopped operation there. Also mentioned Sleipner in the North Sea. You can see here the platforms, and this, this is the working platform where they capture the CO2 and then they re-inject it through pipes, and that's been operating for about 25 years now at about 1 million tons per year, going into a formation. You can see here, they show, you can have these saline formations under land, but you also can have them underwater. So that's some of the experience that we have. So what are the challenges? You already brought up the thing of induced seismicity. Another couple ones, I'll come to those in a minute. Let me start at the top here. So cost obviously is one thing. The cost of transporting and storing the CO2, it will vary. In general, it will be a smaller amount of the cost of the total operation than compared to capture. A rough order is 80% capture, 20% storage, but that can vary quite a bit. Infrastructure, and this is moving the CO2 around. So this is a map. This is a little old. This shows 3,400 miles of pipeline in the United States. We're closer to 6,000 miles of pipeline now. A lot of the pipelines developed, these here, Sheep Mountain, McElmo Dome, Bravo Dome, these are actually natural reservoirs of CO2. So just like you have natural gas reservoirs. And natural gas reservoirs, it's mostly methane, but it has other things in there, including CO2. Well, these reservoirs are predominantly CO2, and so all they have to do is take it out of the ground, compress it, put it in a pipe, and ship it to the oil fields of West Texas here or along the Gulf Coast to put it in. Some of the sources of the pipeline, this is a cement plant here, and Labarge is that's not a cement plant, that's ammonia plant. Labarge is a natural gas cleanup operation. This is Beulah here is a coal gasification plant. So there's various sources going on there where this pipeline network has developed mainly to support the enhanced oil operation. People also talk about doing ship transport, and it's a big project. Yeah, go ahead.
So sorry to step back, but
Go.
you were saying basically that's back. That's something that's being looked at for
Renewable.
fuels.
You mean like hydrogen or something, or?
Well, hydrogen, they find
So, I mean, what type of fuel specifically are you thinking of?
Anything,
So, if they're liquid fuels, the answer's probably not. These are gas storage, pretty much. They are, I mean, hydrogen does use it, but hydrogen in these type of reservoirs does not work that well. It's a small molecule. It, you know, it doesn't behave quite the way. But what they are looking at for hydrogen is another type of thing is salt caverns. So you have these salt domes, and you can solution mine them and make a cavity in them. And that's what they are using those for hydrogen now. For liquid fuels, you know, there's about 1,000 to 1 ratio on density between a gaseous fuel and a liquid fuel. And so the liquid fuels you can pretty much store in tanks above ground and don't need the volumes that you see underground. Okay? So I was talking, you can also do this by ship, and there's a project in the North Sea called the Northern Lights Project, where they're actually looking at ship transport of CO2. They're going to gather it from around the North Sea, bring it to a site on the shore of Norway, offload it, and put it in a pipeline there and bring it offshore for injection. The cost of that's quite expensive. So give you an idea, transport and storage of CO2 using pipelines, which includes the storage in the ground, maybe runs $10, $15 a ton of CO2. If you're going to do it by ships, some of those numbers are running up $50 or so a ton of CO2 and maybe even higher. So ships are very expensive, but that's the Europeans sort of have a little adversity to storing the CO2 underneath them, onshore, so they've been going offshore. Whether they'll scale that up and continue doing it is still questioned. So, you know, this brings us to what's the capacity and the long-term integrity. So going back to, you know, long-term integrity is important. You don't want it to leak out for a number of reasons. One is if it leaks out, you spend all this money to keep it out of the atmosphere. If it leaks out, you basically wasted your money. The other thing is, can it cause harm to people? CO2 is an asphyxiant, so it's, as I said, in the ground, it's buoyant. It's less dense than water, but once it hits the atmosphere, CO2 has a molecular weight of 44. Air, which is nitrogen and oxygen, molecular weight 28 and 32. So CO2 is heavier than air and tends to, hug the ground. Eventually it disperses. But if you have a leak where there's topography where it can accumulate, then there could be a problem because CO2 is non-toxic, it's non-flammable, but it is an asphyxiant. They use it in fire suppression systems, for example. So you don't want that to happen on the leakage. There was recently, I think, 2 years ago, there was a pipeline leak in Mississippi of a pipeline with CO2, and it also had H2S in it. And that's because it was you know, I mentioned in Alberta they had H2S and CO2 acid gas. Well, they had that in Mississippi also, but they were pipelining that to put for EOR. And with the rupture, no one got killed, but quite a few people got sick. But it was mainly from the H2S. So, you know, the question is, you know, you really, and capturing CO2 from a power plant or other plants, you really don't get H2S. It's only from oil operations. And so that's another consideration. And so keeping the H2S out of these pipelines makes it much safer. Go through some of these other things in these slides here. So in the IPCC report, one of the biggest, a couple of the biggest challenges was what to say about the long-term integrity and the capacity. And there's quite a few fights over the exact wording, and this is the wording that we came out with. It says observations from engineered and natural analogs, as well as models, suggest the fraction retained, so that's the opposite of leakage, in appropriately selected and managed geological reservoirs is likely to exceed 99% over 100 years, and likely to exceed 99% over 1,000 years. Very likely over 99 years, so this is saying it's very likely less than 1% will leak over 100 years, and likely over 1,000 years. Very likely in the IPCC speak means 90% chance, and likely means about 60 or 70% chance of it. So it's, you know, the expert opinion from that report was leakage will be very minimal, and even if it does leak, it's a minimal health risk, unless, of course, if the leak is large and you're in a topography where it can accumulate. But that's really quite unlikely. If it does leak, you can sort of think of the sandstone like a sponge, as opposed to a water balloon. And so if it leaks, you know, water in a sponge, you have to really squeeze it to get it out. Water balloon, you pop, it blows out like that. So it's more like a sponge in there, so you won't get these massive leaks. And this has pretty much been confirmed by the projects we've seen so far. We really haven't had any leaks from these underground reservoirs. The worst thing that's happened is that pipeline break in Mississippi. Capacity, once again, there was a lot of questions on this, and it's hard to say capacity. The amount of pore space in the earth to hold the CO2 is more than we'll ever need. But you know, how much of that can we use? As I say, because the pressure limitation that limits how much of the pore space we can use. And back in 2005, we said a potential of at least 2,000 gigatons of CO2 storage in geologic formations. We put out 40 tons a year of CO2. So if we did all the CO2 from energy use, we can put 50 years in it. Of course, we're not going to do that. So we have centuries probably of storage capacity, even at this low level. And some more recent numbers are bigger. The U.S., for just the U.S., they have an atlas, and they had a range of basically 2,000 to 20,000 gigatons. I think the 20,000 is probably a little too big, but there's quite a bit. We did some work, paper that we put out, my group, in 2017. This is sort of we looked at storage capacity. So storage capacity, there's a lot of it, but it's not, these are the sandstone formations, so the darker the color, the better the storage. You can see here in the U.S., the Gulf Coast is very good. You have some offshore here in the Mid-Atlantic and Northeast. There's a big saline formation underneath the Midwest. And you can see there's throughout the world, but there's lots of areas that are also white that don't have it. India, for instance, does not have a lot of sandstone formations. You know, countries that don't have a lot of oil reserves will not have this. So sandstone formations are a lot associated with oil reserves. Japan, Korea, they don't have a lot of opportunities to do carbon capture or storage there. Japan has an idea. What they want to do is sort of create like hydrogen and bring it to Japan, where they make the hydrogen from hydrocarbons in, say, Saudi Arabia. They have a big project, and hydrogen is not that easy to transport, so they want to actually make ammonia, which is the hydrogen carrier. So they'll have these big plants in the desert of Saudi Arabia using renewable fuels, or if they want to use hydrocarbons, they can do the capture and storage there, and then they'll ship it to Japan. So each country, you know, has unique situations. I mentioned basalts, And you can see here where we have, well, some of the purple and also these ridge lines are places that we can maybe use basalts. There's a project in Iceland called Carbfix. So up in Iceland here, you got the big star. They're actually injecting CO2 into these basalts, and that works a little differently. First of all, they dissolve the CO2 into water. So now you have CO2 dissolved in water, and then they inject it in the ground. And then with a year or two, it actually reacts with these basalts. They're very reactive, and you form carbonate rocks. So you get pretty permanent storage. But they've only been doing it on a very, very small level up here. There's been also some experiments in the Pacific Northwest. I actually was at a meeting a couple weeks ago and talked to some people in Kenya here in the Rift Valley. They're actually having a project to look into basalts. So this is an emerging field. We'll see. I mean, it works on a small scale. The question is, can it really be scaled up? So you also have regulatory issues with geologic storage. Some of the legal issues is who owns the pore space. In Europe, it's really the government that owns it, but in the U.S., depending on the state you're in, it could be the surface landowner, so the land under people's property, or it could also be the property rights owner, and different states have it differently, and there's actually been quite a few laws passed in the U.S. over the last couple of decades trying to clarify this in certain states that have been sort of leaders in doing geologic storage. You need an injection program. The EPA has something called the Underground Injection Control Program, where anytime you drill a well to inject something in the ground, you need a permit from the EPA. Enhanced oil recovery operations have operated under what's called a Class 2 permit. I think a Class 1 permit's sort of the biggest permits they have. Like in Florida, they inject a lot of wastewater in the ground. Those are Class 1 permits. And they created a new class for CO2 injection wells called a Class 6 permit. So when we talk about some tax credits later on, to get those and inject in the ground, you're going to need these Class 6 permits from the EPA. And one of the issues here is federal versus state. The EPA has been notoriously slow on granting these Class 6 wells. There's several of them that have been granted. There's one in Illinois for Decatur project, for instance. But under this program, a state can establish primacy. That means the state can actually issue the permit as long as their regulations are at least as strict as the EPA's regulations. And to date, 2 states have primacy for these Class 6 CO2 injection wells. That's Wyoming and North Dakota. And my understanding is it's eminent for Louisiana to get that also. I know Texas has applied for primacy also. So I think the states that are going to be doing a lot of injection will be looking to get primacy and regulate it that way. Long-term stewardship is an issue, and that means once we put it in the ground and leave it there, it's going to be there. What happens? What happens 10 years, 20 years? Or how do we also ensure that it's not going to leak? So in the EPA regulations, they say you have a 50-year period after injection stops to monitor it and make sure everything's well. But who's going to take the liability if something happens? There's talks about ways to do it through private insurance. Also talks about the government taking over liability. And in some states, they already have passed laws that the government will take over the liability. The chances are small of things happening. Once you stop injection, and the longer it goes, the less and less chance of leakage that happens because the underground mechanisms I mentioned of dissolving the CO2 and precipitating out carbonate rocks. So we see what happens there, and then also how you get credit under climate regulations. And we'll talk about this in the last segment, the tax credits that you can get and how the rules are written. Other issues, you know, there's, when you do these projects, there's can be multiple regulations, so people are trying to look to unify them so you can just get everything in one place. We're not there yet. The regulatory requirements, some people think the EPA rules are a little onerous and they don't encourage things. I think the 50-year period is too much. So I think they're looking at trying to still figure out what's the right waiting period and what's the right amount of monitoring and verification you need to do. And as I mentioned, the public versus the private role. Can we do all this through the private sector, or this government has to be involved in taking some of the risk off of the companies? So those are some of the issues that this faces. We're still early on, but we do have projects where we are injecting underground. As I mentioned, there's a site in Decatur, Illinois, that has a Class 6 well. North Dakota has several projects that are either started or they've applied for permits to be a repository of CO2. And the government has a program called the Carbon Safe Program, where they're trying to develop storage reservoirs. And I think what will happen eventually is you'll see regional storage reservoirs, so every single project doesn't have to worry about figuring out where to put the CO2, but can take their CO2 to an already established storage site. So, similar to what we do today when we have our garbage picked up and taken to a landfill. So, stop there for a moment before I move on. Any other questions? Okay. We'll look at CO2 utilization. I'll talk about the markets. There's two types of markets. We have the liquid solid market and the gaseous market. We'll talk about EOR and CCS, what the role is, and we'll see if there are other markets beyond the markets we have today for CO2. So the way CO2 is produced today is there a lot of small CO2 production plants. They're on the order of 100 plants, and why is this? CO2 doesn't travel well in small quantities. So the transport costs can get pretty high if you're going more than a couple hundred miles from where the CO2 is produced. And where they have these plants are where there's good opportunity for the CO2, a good feed stream for the CO2. What do we mean by a good feed stream? Like I said yesterday, a feed stream that has very high concentration or CO2s under pressure. So if we look here, in 2010, we had a capacity of about 11.3 million metric tons of CO2 per year. Once again, very small compared to the 6 billion tons of, maybe more like 5 billion tons of CO2 that we produce from burning power in the United States. The average plant size is only a couple hundred metric tons per day. And we see here the different sources. So there are four main sources, I think, that are shown here. You got ammonia production. So ammonia production is like a pre-combustion captured. You have a synthesis gas. The natural wells from gas processing, which come out of the ground at high pressure. Hydrogen production, which we went over yesterday, once again, high pressure stream that they can use. And fermentation byproduct, these are ethanol plants, and the ethanol plants are basically close to 100% pure CO2. That Decatur I mentioned, it's coming off the fermenters, pretty much 100%. They don't do any purification. It's put right into a compressor and then right into the ground. I should say that there's a major project trying to be done in the upper Midwest, a company called Summit Energy. It wants to, there's a lot of ethanol plants there. Go take a look here. You can see the blue dots. So there's a lot of ethanol plants right here. And what they want to do is connect them by pipeline and take all that CO2 up into North Dakota here and inject it there. And they with the tax credits that are in existence today, it can be a profitable project. The biggest problem is getting permits for the pipeline, and Iowa has been the real bottleneck there because of the way the regulations are. A single landowner can really cause trouble in the pipeline. So all of that is being played out right now, and it's been ongoing for a couple years. Summit Energy is still pretty optimistic they'll get everything built, but that's an example. But you can see how the plants are things. You have the ethanol in the Midwest, hydrogen plants, a lot around a lot of them are used for refineries. You have natural wells. We saw a lot of those where those pipelines were built before, and and ammonia plants. Once again, we see here a lot in the Midwest. What's CO2 used for? Biggest thing is the food industry, beverages. We understand beverages or carbonated sodas. The food industry uses a lot for flash freezing, among other things. That's one of the big uses. You can see other ones that are here. But food and beverage make up the biggest uses. And once again, it's not that, you're talking about millions of tons, not the billions of tons we put out. The food grade CO2 prices, and we say by food grade, we mean very high purity CO2. There are different things, what purity you need. If you're putting it into beverages, you need very high purity. You don't want to have any impurities in your Coca-Cola. People will taste it and they won't buy your product. And so the prices, basically, could be a big range, and these are delivered prices, so some of that because of longer transportation, but typically is $50 to $90 a short ton. When we come back to cost at the end here, we'll compare it to what things cost, but but to get it, say, to capture from a power plant today will cost you more than this range. So it's like, plus you don't want to do, if you're doing it for, to get it out of the atmosphere, if you sell it into this market, most of these uses, they're going to put it right back in the atmosphere. So that doesn't help you. The gaseous consumption, and most of the gas is from these natural wells, the things I showed you, the Bravo Dome, Sheep Mountain, and most of this is used for enhanced oil recovery, some for urea. Basically urea is made as a combination of ammonia plus CO2, and it's used for fertilizer. Sometimes you use ammonia directly for fertilizer, but sometimes you make urea, which is a little easier to apply. You can see how much has been used, purchased for EOR. So we're probably up about 50 million tons a year of this gaseous CO2 going into the ground for enhanced oil recovery. The pipeline prices, once again, because you're pulling out of the ground, it's fairly cheap. The people that use it for EOR, they drive a tough bargain. They're not going to give you 1 cent more than you want. And the typical range of prices about $10 to $16 per metric ton. If you go into literature, people sort of back calculate, say, well, if you're using this to get enhanced oil, you know, obviously the oil price is higher, you can pay more for the CO2, and they have this formula here of dollars per 1,000 cubic feet of CO2 is 2% times the dollars per barrel. So if we have $100 a barrel oil, it's $2 per 1,000 cubic feet, which turns into $36 per metric cubic ton of CO2. People thought when the oil prices was high, well, this is an opportunity, but the market doesn't really work like that. They don't really use this formula. It's a supply and demand, and I know a number of projects that were trying to get financed, and they were disappointed they were not getting this type of money, but were getting offered that type of money. So, why EOR? A big criticism of carbon capture is that a lot of the work has been done for EOR. You know, a lot of the projects use EOR, and one reason for that is we don't have markets, other markets for the CO2. It's a way to help with the project financing. Instead of having to pay someone to take your CO2 away, you actually get a little money for it. So in the short run, it's been very helpful. It's helped build up the infrastructure, but in the long run, you're really going to have to get away from EOR. First of all, there's not enough storage room in these active oil reservoirs, and secondly, if we're doing this to reduce carbon, we really don't want to use the CO2 that we're putting in the ground to generate more CO2 from oil that we produce. So what can EOR do? It helps the project economics, it helps us build out the infrastructure, develop capacity along the supply chain, and it's also helped shape the regulatory environment, including liability issues. We understand the issues with putting CO2 in the ground, you know, what type of risk there are with it. But it's not enough money from EOR, as I said, to really help us capture from what we called yesterday the dilute sources, and it's not going to replace climate change as the primary driver for carbon capture. So it's very limited how much carbon capture you can do with EOR, but climate change, we're going to need to go order of magnitude or two, probably a couple order of magnitudes above what we're doing for EOR. Talk about other things you can do with the CO2, and you know, people always ask, can we utilize it? Because we always want, if we can use it and get some value from it, it's always better than storing it in the ground, than basically burying it. But to have a significant impact, it has to operate on a large level, and it also needs to make something that's not going to go back in the atmosphere right away. So you need some long-lived products. One thing people talk about is conversion to fuel, and another thing is converting it, or what they call mineralization, converting it to cement or rock. And if we look at thermodynamics of it, and we have, this is the free energy of formation, so CO2's here. If we go this way, we're going downhill, so this is thermodynamically positive way. So thermodynamics worked with us, and you can see here, this is where we can do mineralization, so that's why there's a lot of interest in mineralization. You do need to supply alkali for this process, and I'll talk about that in a minute. If you want to convert to fuels, so here's, say, going up to methanol, you're going the other way, and you're going to have to put energy into the into it. So let's talk about converting to fuel. So here's methanol. When you burn methanol, you get off energy, create CO2. Now, if we want to take it back the other way, we have to add that energy back. But not only do we have to add this amount of energy, you have to have more energy, probably 50% more. And the energy better be carbon-free. So if you have this much carbon-free energy, at least at this point in our decarbonization, it's going to be much better to use this to knock out the use of fossil fuels in the first place than trying to recycle this around. I'll talk a little about fuels. People are worried about fuels, how do we decarbonize it? And I'll talk about that a little later. But and the other problem, of course, in doing it this way is when you burn the methanol, you're going to release CO2 into the atmosphere. So it's not really getting rid of it, but it's sort of using it twice instead of once. Yeah.
What's the, what, like, the
What are the processes?
yeah, like, kind of what that.
Well, there are different ways to do it. A lot of times, in general, a lot of times to go from a small molecules like CO2 into bigger molecules, you want to create a synthesis gas. So you want a gas that has basically carbon monoxide and hydrogen. So you may have some reforming process in there, and then you go through, if you're making a liquid fuel, like a Fischer-Tropsch process. Fischer-Tropsch, it's basically a catalytic process that allows you to make big molecules out of small molecules. Mineralization, as I said, it goes downhill, but theoretically it looks good, but it's been very hard to replicate this in reality. You need large amounts of material required. So, as I said, you need alkali. So a lot of times they'll use these silicate rocks, like olivines or serpentine, which are magnesium silicate rocks, and you need to, the reaction rate is slow. Nature uses rock weathering to remove CO2 from the atmosphere over time. It's a slow process. It acts on about 100,000-year time scale. But so you need to get the rates up, so you need to really crush the materials a lot to get a lot of surface area, and you may need both heat and pressure to get the reactions to move. So that becomes very expensive. There's been programs at the Department of Energy to try to do this, but they sort of gave up doing what they call ex situ. But there's interest in this, in doing it in situ, and also for capturing CO2 out of the air. So I'll come back. I have it here. Yeah, so I'll come back to that when we talk to the next module, when we talk about capturing CO2 from the air. All right, so this is just a summary, I think, of everything I said. I think on mineralization, people with the cement industry, people are looking at basically making cements that absorb CO2. So the original thing where people thought that you can just turn CO2 into rock isn't really approaching, but there's some spin-offs from this that people are looking at today. But the bottom line is large-scale storage in underground in geologic formations is still going to be required to get us to the gigaton scale. So how are we doing on time? Let me just, I'll start the biofuels quickly. I probably won't cover all the slides, but let me just give an overview here. So fuels, people look at fuels as a couple reasons of interest. It's hard to decarbonize the transportation sector, which uses fuels. Electric vehicles look like they're going to do the private autos, but that's only about half the CO2 coming out of the transportation sector. How do we take care of the arrest? What type of fuels do we use? And the other sectors here I list: air, long-range trucking, shipping. So people are looking at different options on how one can do this. One idea is offsets, that we go ahead and still use the hydrocarbon fuels on these modes of transport, especially airlines, but then we offset them with negative emissions, which we'll talk about in the next module after the break. Another is biofuels, where we use basically biomass. Here the CO2 once again start in the atmosphere, and the biomass captures it, and therefore if we turn that biomass into fuels, we can do it. We can do it biologically or thermochemically. We're actually doing biofuels today. Ethanol, which is about 10% of our transportation fuels, have ethanol. Ethanol represents about 10% of our transportation fuels from all those ethanol plants I showed. So that's a biological use, but there's other pathways to do on a bigger scale. People talk about thermochemical pathways, and then there's also, people are looking in the future, what they call e-fuels, fuels made from electricity, and that could be hydrogen. You can use electrolyzers to hydrolyze water, or synfuels that are made from CO2 plus hydrogen. Once again, is the type of synthesis we talked about, using a Fischer-Tropsch type of process. I do have a thermochemical pathway example, but I'm probably going to do that after break. But before I get to that, we actually did some work recently. We actually just submitted a paper on this topic here, where we use some models to say, not just our models, but we looked at all the different energy economic models and what they were predicting for future liquid fuels. And things came down into 4 categories. One is basically use our conventional liquids and offset them. And in this square here, they're offsetting it by what's called bioenergy and carbon capture and storage. Once again, we'll go more into detail what that is after the break. Also here, in this thing, we're also talking about using liquids, but now offsetting it by direct air capture. And this column here is, we have no restriction on geologic storage, so both of these, BECCS and DAC, use geologic storage. The difference between these two here is, do we have biomass constrained or not constrained? If biomass is not really constrained, we should have plenty of biomass to do our BECCS. If it is constrained, then we have to look at DAC, because DAC's more expensive than BECCS. Now, if our geologic sequestration is constrained, then In this quadrant, we see biofuels coming to the fore, using the biomass directly as biofuels. And then here, if both biomass is constrained and geologic storage is constrained, then we see these synthetic fuels, basically what they call e-fuels. And if you know, when you look at the models, they don't sort of put in these categories, but when we did it, we dissected a lot of these models and showed that people will fit into one of these 4 categories on the decarbonization of what I'll call the residual fuels that we can't really mitigate directly, that we don't have a good substitute for, and they'll fall in one of these 4 categories. And we actually developed a little simple model that also showed this. So next section, we'll talk about the offsets here. I do have a little thing on biofuels if we have time for it. And then finally, I'm not going to go into synthetic fuels. This is by far the most expensive pathway. So it's 3 o'clock, and why don't we take our break here, and then we'll come back. And I'm going to, for now, skip some of the more details on the biofuels. I may come back to it, but we'll go into the negative emissions section next, and if we have time, we'll come back to the biofuels. Okay, so we'll see everybody in about 15 minutes. And if there's any questions, feel free to come up here.